afternoon. Today we're going to tackle one of the most important ideas in calculus in terms of looking at derivative. What the heck is a derivative and how can we use it to figure out instantaneous rate of change? Because that is what we're going to be looking at in calculus until we get to integrals, which is a very large part of calculus, but we're going to spend most of our time this year in the idea of derivative or in the derivative world. Now, a couple days ago, we spent some time on the idea of how to find the slope and equation of a secant line. So a secant line is this green line that meets our graph at 2 points. What is the slope of this line? Well, I'm not going to calculate it right now, but we know slope is equal to delta y, the change in y over the change in x, which we know to be rise over run. And we will write this as y2 minus y1 over x2 minus x1. Hence the difference of the y coordinates divided by the difference of the x coordinates. We can take a look here. Difference of our x coordinates is 1. Difference of our y coordinates looks like it is about 4. So we have a slope right now of our green line of 4. Now, what's more important for us is what is the slope of that purple line? Well, we can see that it gives us to us here. Slope of our tangent line is 2. Now, how do we use the idea of our secant line and our tangent line to help us? Well, we talked about this on a couple days ago. What happens as my graph gets closer, as my point, my x value here gets smaller and smaller. Well, we can see the slope of the green line starts to become closer and closer to the slope of the purple line. Going back to our function here, the difference in the x coordinates, x2 minus x1, is approaching 0. So delta x is approaching 0. Now, as we are talking about the infinitesimal in this part or in calculus a lot of the time, this delta x just means the difference in the x coordinates. What happens as it gets closer and closer to 0? And we can see we're at 0.29 right now. Down to get down to 0.04. I'm really close, and you can see that slope of the green line is starting to get very close to the slope of the purple line. I can't actually put it up there because my computer's being a pain in the posterior, but that's the idea, and that leads us to our definition. Okay. The slope formula is delta y over delta x. Now, instead of y1 and y2, so this would be y2 minus y1, f of x is our function. That's our that's our y2 point, and y1 is our f at whatever point we're looking for. So we've replaced y2 minus y1 with our function notation for the same thing as we make the value a closer to x. So what's happening with the x minus a becomes 0. So the slope, about the limit, this m is the slope of the tangent, is defined as the limit as delta y over delta x, the limit as delta x approaches 0 of delta y over delta x. Replacing delta y with some function notation and replacing delta x with some x minus a, which is basically our x and our y coordinates. A is our first coordinate, our first x coordinate, and x is our second x coordinate. We now have the the definition of the tangent line. I want to say first principles, but it's not. So here's the question. Find the slope and the equation of the line tangent to this function at the point A is equal to 1/2 over 7/4. Now, visually, we know we can sketch 2 minus x squared that looks like that. And we're looking for the tangent at this point, 1/4, 7/4. Now, we can see that looking at my graph, I better get a negative slope because that makes sense. Okay. So we're just going to retake this definition. We're going to put in some stuff. So m, the slope, is the limit as x approaches a of f of x, which is 2 minus x squared. And our f at a is our y coordinate of our function, which is 7/4. And our a value, or this a value is 1/2. So we're going to have x minus 1/2. Little bit of algebra work. Limit as x approaches a of, as x approaches 1/2, I should say. So I can't just plug that in because that would become 0. And we can't deal with that. So we have 1/4 minus x squared over x minus 1/2. I still can't evaluate because I'm going to end up with 0 on the bottom. So let's see. I got factors up top. So the limit as x approaches 1/2 of 1/2 minus x, 1/2 plus x over x minus 1/2. Now, can't cross off directly, but we can see that if I change the signs, I would be able to. So the limit as x approaches 1/2 of negative 1/2 plus 1/2, or 1 plus x. Now, hey, I can evaluate. I can plug in 1/2. So this is equal to negative 1/2 plus 1/2, which is negative 1. Which makes sense in terms of our function, our little sketch that we did. We should have a negative slope. That is all we have to do. No, that's what we do with this definition of the slope of a tangent line. We have to do our limits. Once you get to here, you plug in what you need and work through it. So the slope of this line is negative 1. What do we need to calculate or to figure out the equation of a line? We need the slope and 1 point, and that's what we have. So we have our slope will be y minus 7/4 over x minus 1/2, and that would be equal to negative 1. Just going to solve this. We have negative x plus 1/2. And if I wanted it in y-intercept form, I would add 7/4 to both sides, which would give me negative x plus 9/4. Okay, makes, again, this y-intercept makes sense. It's above 2. If I wanted it in standard form, I would just go x plus y minus 9/4 is equal to 0. So I would have 4x plus 4y minus 9 is equal to 0. Because our standard form, we tend to not like fractions in them. You're going to see the answers in the textbook look like that. Okay? So the definition is how we get the slope of the tangent line. And then we go back to our finding equations of lines that we used in grade 10. Now, I know mine might be slightly different than what Mrs. Lowy does. I believe one of the things that she does is y minus 7/4 is equal to negative x minus 1/2, which is exactly the same thing as I would have done here. this, I believe, I don't remember what the term is called, but it's just a different form. I happen to like fractions. There are a couple different ways. That's the way I like to do it. We could also do y is equal to mx plus b and get the same answer where we would say y is equal to negative x plus b. We have our points. 7/4 is equal to negative 1/2 plus b. Solve for b. We're going to get 9/4. So, like I said, there are different ways of doing this. They're all based on the similar principle. Okay. Now, while I happen to like this and do it quite well, some of the notation that we use is a slightly different one. And you've seen this with, I gave you one of the limits, is we use h. Why? Well, it's a little easier to work with in a lot of cases. Particularly rationalizing the denominator, it is much easier to work with. Same with some rational expressions in a limit. So what we do here is we define x minus a, so the bottom of our function here, bottom of our definition, we define that as h because it simplifies the denominator. And then x, by solving this guy for x, we have x is equal to a plus h. So what that does is it gives us, instead of, well, we'll take f of x minus f of a, which is we had over x minus a. This now becomes the limit as x as h approaches 0, which is what we're looking for. And I'll replace that f of x with f of a plus h. And I won't replace that guy. I'll just leave him as f of a over, and then we have our h. So there's our another definition. Okay. As I said, it does work particularly well for rationalizing the numerator and rationals, as we're going to show here. Now, so we're saying a is equal to 3, and this is our function. Now, I could quite easily say a is equal to 3, and the point is 3, 1, and plug that in. I'm not going to in this case. I just plug 3 into here. I get the y coordinate. I'm going to actually work with the function because I want to work with the function. So m is equal to the limit as h approaches 0. So I'm going to replace the x here with a plus h. So 3 over a plus h minus 3 over a over h. Now, again, if I try to quickly substitute h in or 0 in for h, oh, look, we have something over 0. I don't care what the something is. We can't go any further. So here, let's tidy up that top a little bit. And by the way, please do not forget to bring down your limit notation. I know it's a pain, but that's the process. What I'm going to have is 3a over a plus h, minus 3 a plus h over a plus h. And for tidiness sake, I'm going to write the divide by a as the divide by h as 1 over h. So okay, you can see why I'm doing it. It just tidies it up a little bit. When I look and simplify this top limit as h approaches 0, we have 3a minus 3a. Oh, that disappears. So that we have 0h minus 3h. So we have negative 3h there. On the bottom, we have a plus h, and then times 1 over h. Those guys will cross off. Now, if I plug in h is equal to 0, I get, I'm going to drop the limit now. I have -3 over a plus 0, -3 over a times a, -3 over a squared. Now, what the heck? There's a little bit of algebra for you. I could have done it. I'm going to do the next one a little bit simpler. Since a is equal to 3, our slope at 3 is equal to -3 over 3 squared, -3 over 9, -1/3. So our slope is -1/3. Now we want the equation. Line, we know the slope, we know the point. I found it here. So we have y minus 1 equal to -3, x minus 3. Again, I'm doing a slightly different way than before. And there's my standard form. If I wanted my y-intercept form, -3x plus 10. Now, thinking about this, I probably should have plugged in y, a is equal to 1, or y is equal to 1. I should have just plugged in 1 there. I went ahead where I want to be right now, but that's generally the process. The algebra process is what we wanted to look at here. Okay. This one I'm going to do the other way. Again, using this notation. I don't really have a problem using the other function that we talked about on the first page, but it does make the algebra more tricky. So that's why we've done this. It just means the algebra becomes a little easier. You don't have to worry about x minus a. It's just equal to h. So our slope, we want the equation of the line perpendicular. We'll talk about that in a minute. What we need is the slope of the tangent. First, we need the slope of the tangent. Talk about him in a minute. So here's our equation. M is equal to the limit as h approaches 0 of, so instead of, I'll have my a is 12. I'm going to substitute that in, so we're going to have the square root of 12 plus h, replacing the x in here with 12 plus h, and I'm replacing the a with 12. So there's -3 minus, again, now we have the square root of 12 minus 3. I don't even need that. I can just say 9, or I can just say 3, because when I take my 3, plug it into here, sorry, take my 12, plug it into here, I get 3. And then on the bottom, I will just have my h. Can't evaluate, h becomes 0. Well, we have a radical on top. Let's go ahead and rationalize this. So I'm just going to gather a little bit. So this becomes 9 plus h plus 3 on the bottom. 9 plus h plus 3. So again, this is what we end up with on the top. This times this is 9 plus h. This times that, and that times that, cancel each other out. And I have minus 9. And on the bottom, I have h square root of 9 plus h plus 3. I have the limit as h approaches 0. That 9 and that 9 will cancel off, or will become 0. Therefore, that h and that h will cancel off. Now I've got the limit as h approaches 0 of 1 over square root 9 plus h plus 3. Plug that in. I have 1 over 3 plus 3. I have 1/6. Okay, so there's your slope. I could find the equation of the tangent line at that point. Okay, well, here's our function. A version of our function. We're here. We're way over at 12. Okay, that makes sense. That's a fairly flat line. Now, it says the line perpendicular to the tangent. This is where we have to reach back in our memory. If I want the line perpendicular to the tangent at 90 degrees, this slope is 1/6. This slope is -6. It is the negative reciprocal of the original tangent. So 1/6 times -6 is equal to -1. Hence the idea of a negative reciprocal. So that's just that next wrench I threw into the system. So the slope of our slope of our line perpendicular is -6. So we have y minus 3 equal to -6. X minus 12. Y minus 3 is equal to -6x plus 72. And there is our line perpendicular to that tangent at the point 12,3. The only thing that's different about that than the last two questions is I asked you for the line perpendicular. Extra little bit of work to throw in. This is the most important part. How do we do this? How do we use this definition to solve our question? Okay. Now, this is the one that I kind of did on that last, on the second question. This is the slope of the tangent function. So we're finding at any point a square root a. A being a function, square root a being the output of that. A being a number, square root a being the output of that number. Using this definition, we will replace x with a plus h. We'll replace f of a with minus square root a over h. Now it's just a question of manipulating this to get the equation that defines the slope, which I did 2 questions. Okay, I gave you this is the equation in terms of a, and then I plugged in my a value to get my slope out. We're going to do the same thing here. So m is the limit as h approaches 0. Well, we have this radicals on the top. We're going to do our conjugates multiplied by the conjugates. Okay, so essentially, if you see a radical sign on the top and you're doing limits, you're going to have to multiply by the conjugates. If you see a radical function, a rational function, you're going to have to simplify the rational. If it's a polynomial, you might be able to get away with just factoring. Should be able to get away with just factoring. So our conjugates, what we have is we have a plus h minus a over our h. And I need to not write x plus h. I need to write a plus h. I have a habit of doing that because I know where we're going. Our a's are going to subtract to give you 0. That leaves h on the top. m is equal to the limit as h approaches 0 of 1 over square root a plus h plus the square root of a. I can now go ahead and evaluate at h is equal to 0. So that becomes 1 over square root a plus square root a. This becomes 1 over 2 square root a. And that is the slope. My pen decided to die. That is the slope of any point. So we have our function square root a. If I wanted to know the slope at this point, I would just plug in that value of a into here. I would get out a particular slope. If I want to know farther along at, let's say, 9, I plug that in. I end up with the slope of that one. And that's it. Now, this is going to lead us. How the heck do I don't have to do this anymore? We will get there in a day or two. How do we do this without having to use your definition of a derivative? Okay, so I'm just going to have to do these with my fingers. Annoying, but it is what it is. Please excuse the messy writing. Find the slope of the tangent, so find the equation, because we're looking at x is equal to a. Okay, using the definition, m is equal to the limit as as h approaches 0. So our function here, we're going to use the definition. I'm not going to bother writing it out, but we're going to use this one. So I'm going to replace x with a plus h and a. So I have 2 over a plus h plus 3 minus 2 over a plus 3 over h. There's our definition. I have rationals at the top, so I'm going to have to simplify them in some way. I'm going to do that by writing them as with a common denominator. So I have 2a plus 3 over a plus h plus 3 a plus 3. It's not my limit. Limit h approaching 0. And I'm going to write again my h as 1 over h just for tidy. No, I'm not going to do that yet. So much easier if I didn't have to write my finger. Minus 2a plus h plus 3, and then times by 1 over h. Again, I'm sorry about the writing. Okay, so looking at our top, we have 2a minus 2a, so that disappears. We have 6 minus 6, that disappears. So our limit h approaches 0 of h on top over a plus h plus 3 times 1 over h. Our h will then disappear, which allows us now to evaluate, and we're going to end up with 1 over a plus 0 plus 3 times a plus 3, 1 over 2 a plus 3. Again, I'm really sorry about the messiness of my writing, which is even worse than normal. there's the equation that defines the slope of that function at any point A on that function. Oop. I did miss a 2 here. So there should be a 2 there. Now, this next one, not that bad. Again, we're just going to have to do some work. So we have the limit as h approaches 0 of 40 a plus h. I'm going to go to a different page because I'm running out of room. Limit h approaches 0 of 40 a plus h minus 16 a plus h squared minus, in brackets, minus 40a minus 16 squared all over h. Now, again, what the heck is this? Well, this is just simple. We have a little bit of work to do. We have some algebra to perform. That works out to be 40a plus 40h. This works out to be 16a squared, and we'll put brackets around that, plus 32ah plus 16a squared. Again, all I'm really doing here is some skipping of some steps with my algebra. I squared a plus h squared and then multiplied by 16. And then this guy minus 14a minus 16a squared. Well, that's 40a. We're going to cross off with that 40a. This minus 16a squared is going to cross off with that minus 16a squared. And as I usually do, I forgot a line by h on the bottom. So what I have is limit as h approaches 0, 40h minus 32ah plus 16h squared. That's all I have left on the top. Now, on the top, I see I have an h in every term. That leaves me with 40 minus 32a plus 16h. Those guys disappear, probably cancel each other out. And now we're able to evaluate. I plug in instead of package. So what I have is the 40 minus 32a plus 16 times 0. And therefore my slope is described by the function 40 minus 32. Again, doesn't matter where on that function we're talking. I could find anything. If I wanted to know the slope at 0, plug in 0. If I wanted to know the slope at 16 seconds, I would plug in 16, and so forth. Again, I'm going to go over this with you tomorrow. I'll give you some more, probably do some more examples. So question number one, I want you to use the original. Question number two, I want you to use the one that I've been using the last three. And like I said, I will go over many of these with you tomorrow. Hopefully my voice sounds better by then.